Okay, welcome to part 2 of the Rankine cycle video. So today I'm going to do a little example of a Rankine cycle calculation. So this is going to be our Rankine cycle example. And again, there's numerous variations of this. There's different things we can do to the cycle when we turn it into a real steam cycle, different data that you can provide it, but you'll get the general gist on how to actually tackle these problems. So first of all, we're going to show the circuit that we've been provided with. So we have a boiler providing steam to a turbine. The turbine's actually going to do some work, and then it's going to bring out a saturated vapor. That's going to go to our condenser, where it's going to be cooled. It's going to come out the condenser, and then it's going to go to a pump. We're going to put some work into that pump, and then it's going to provide that pressurized water to the boiler. So we're going to label these components. So we've got a condenser. That's actually dumping heat out. We've got a boiler here with Q going in. Call that the Q boiler. And let's label that boiler. We've got a turbine. And we've got a pump. I'm going to label some stations as we go around. This is station 1, station 2, station 3, and station 4. We're going to have work out of the turbine. Let's call that work out the turbine. And we're going to have work going into the pump, and WP. So for this particular plant, we're given some data. So provided with a mass flow, so that's the mass flow flowing around the steam, equal to 25 kilograms per second. We're going to provide it with the pressure out of the pump. So 2 is going to be 5.5 megapascals. Pressure out of the turbine. So P4 equal to 10 kilopascals. What else have we got? Oh, let's get the, we're given the temperature out of the boiler as well. 490 degrees C. So what we want is find power out, heat in, pump work, and plant efficiency. So this is the question. Once we've got that information, we should draw the TS diagram. So we'll draw the T and the S. We should always draw this. Draw the vapor dome, and then the interrupted pressure lines. So we can start to label some of the stuff. So we know the maximum pressure out is going to be the 5.5. So we know that this pressure here is the 5.5 megapascals. We know this pressure here out of the, well, we can actually draw the circuit in. So we're going to go from 1 in the pump up to 2. This isn't a Rankine cycle, so isentropic. And then we're going to heat the water up and boil it till it's saturated. So that's going to be the position at 3. And then we're going to expand it down. Actually, this one, I've actually gone superheated, so I haven't. This is not a true Rankine cycle. We've actually got a superheated cycle here because this 490 is not on that point. Then we're going to expand down isentropically. So the only thing different here is I've given, it's not a true Rankine cycle. We've actually gone to a higher temperature in this example. And then back down to the condenser here, and then cooled there. So the condenser's dumping heat there. That's your QC. getting heat in here from the cube boiler, and the work into the pump, and the work out the turbine. And so we know that when we come out of the condenser, we're told that 4 is 10 kilopascal. So this here is the 10 kilopascal line. Okay. And we're told that this temperature here, T3, so that's T3, is 490. And I know this is superheated because if I was to look at my saturated tables, so if I go to table A4 and look at the 5.5 megapascal line, 5.5 megapascals, which would be the 5.5 kilopascals, we can see the temperatures here somewhere between 263, I'm not sure if you can see that, I can bring this up, between 5 megapascals, if you look, it's going to be somewhere between 263 and 275. So basically at 490 we're way above this, so we're in the superheated region. So that's how I know. If I didn't know to begin with, that's how I could find out that I'm actually superheated in this case. So that's the problem. Let's go start working our way through. So always a good place to start is where the most data is, but in this particular case, if you're not sure, I always think the pump is one of the easiest things to work with. So we will look from 1 to 2, and we will look at the pump. So I always like to draw a little schematic of my pump. I've got coming in 1, I've got going out 2, I've got some work into the pump. What do I know at 1? Well, at 1 we know it's 10 kilopascals, and we also know by looking at our let's have a look, where are we? We know that's about it, I think, 10 kilopascals. We know 25 kilograms per second. And we know we're coming out at P2 as 5.5 megapascals. From our theory we discussed the other day, we know that the work into the pump equals the volumetric flow times the change in pressure. And for this example, we know that we've got 25 kilograms, so how do we relate 25 kilograms to the volumetric flow? Well, density of water is about 1,000 kilograms, so if I take the 25 and divide it by 1,000, that will give me my meters cubed per second. Remember that mass divided by volume equals density, so therefore volume equals mass over rho, and then if we make it time dependent, we end up with that m dot over rho, which is what I've got here, times the change in pressure. So it comes out at 5.5 times 10 to the 6 minus the pressure that it goes in as 10 times 10 to the 3. So if I work that out, I end up with 387.2 kilowatts. So that is the electrical work that's going to go into the pump. Again, assuming the pump's 100% efficient, we're not told anything else from that. If I do the energy accounting equation, which is kind of redundant now because I've got the work, but the reason I'm going to do it is because I really want to find the conditions of 2 here, the enthalpy at 2. I need 2 properties to go into the combustor. So if we do the energy accounting, plus the work in, plus the m dot energy in, minus the m dot energy out. I'm not storing energy in my pump, I'm not creating energy, there's no heat transfer shown, and there is work, so the work in equals, I bring these two to the other side, m dot energy out minus energy in, which is a h out, h2, minus energy in, h1. So I do know my work already, 387.2 equals the 25 times the h2, which I do not know, minus h1. Let's think about this. What is h1? We know 10 kilopascals. Do I know what h1 is? So it's coming in as a saturated liquid. Okay, so that's what we know. We know that 1 is coming in as a liquid. And in reality, it could actually be a bit little cooler, but if we know the temperature and we know that it's a saturated liquid or a subcooled liquid, we can use the enthalpy at that temperature for a liquid to give us that. So we know at 10 kilopascals, I can go to my table H4, table A5, sorry. So table A5, the pressure table, I go to 10 kilopascals. You might not be able to see this, but if you've got your table A5 in front of you, 10 kilopascals, we go across and we read the HF of the liquid, 191.81. 191.81. So that's my, here, P1, 191.81. So I can solve this equation to get H2 and plug that into the calculator, and we end up with H2 equal to 207.3 kilojoules per kilogram. So it's kind of the cart following the donkey there, because I actually found the work and then I used the work and my first law energy accounting. I could have started with this energy accounting equation and I would have realized that I don't know the work and I don't know H2. I would have had two unknowns. So there would have been a problem with the one equation and two unknowns. But remember this equation for pumps, this works only for the pumps with liquids. That allowed me to solve for the work, and therefore I could then solve for the unknown enthalpy H2. Okay, so that's the pump done. We've got the work into the pump, which is one of the questions they ask at the end. So let's move on to the next component. So what we got next, we have the boiler. So we can draw a picture of the boiler. We've got our compressed water coming in and then our steam coming out. So this is state 2, this is state 3. No harm in putting the data we have, 5.5 megapascals here. For the pressure, we know H2 as 207.3 kilojoules per kilogram. We could actually, with that data, we could find the temperature at 2 if we wanted to. We'd find that it heated up probably somewhere around 40 degrees, still pretty cold. 1 or 2 degrees across the pump would have been the temperature rise. That's possible, doesn't ask for it, so I'm not going to do it. We know that it's going to come out, because we're not told any differently, that the pressure is going to remain the same. In reality, there may be a pressure drop, and we may have to take account of that later on, but at the moment, the pressure doesn't change. We're also told the temperature, T3, is 490 degrees C. So, energy transfers now, when you do your sketch, we show the energy transfers. So we have a Q coming in, the Q, the boiler. It's one of the unknowns we're trying to find. We can do our energy accounting equation for our boiler. We're not storing energy, we're not creating it, there's no work done. What we're left with is that the Q in, the Q of the boiler, equals the m dot times the energy out, which is going to be H3 minus the energy in, H2. So we don't know QB, we do know m dot, and we do know H2. So we really need to find H3. We need this H3 here. This, as we've seen on our TS diagram, is not for a Rankine cycle. We're actually superheated, so we're up here somewhere in the superheated tables. So this is a little tricky. What we've got to do, it's not impossible, just a little tricky, is we have to go and look in our superheated tables, table A6. I'll grab that one, table A6. And we're at high pressure, so we're a couple of pages in the back of your bowl. The superheated tables is presented at different pressures. We are at 5.5 megapascals. Turns out 5.5 megapascals is not here. We have 5 and we have 6. We're also at 490 degrees C, which is also not on the tables. 450 to 500 is what we have on the tables. So we have to do some interpolation, and in fact what we have to do here is what's called a double interpolation. So it's kind of the worst case scenario, but it's not that hard if we lay it out properly. So what we're going to do is we're going to look at our table and we're going to pick the lower pressure of the two. So we'll start with the 5 megapascals and we'll write the data that we can get from that around our point. So at 5 megapascals, so pressure, 5 megapascals, we will have data at 450 degrees C. and data at 500 degrees C. And so we are going to have an enthalpy, and we look in our table, we can read that number. It's always good to write out the numbers so you can check and make sure you make a typo later. And I'm also going to do the entropy here. I'm doing the entropy not because I need it in the boiler, but I will need it for the turbine in the next stage. So I'm going to write the entropy down as well. So that comes out to be 6.8210. If I didn't do it now, I just have to come back and do it later. Then I go to the 500 degrees C and I read the data off there. I have 3434.7 for the enthalpy at 5 megapascals and 500 degrees C, and I have an entropy value of 6.9781. And so I've got the data kind of blanketing the 490 at 5 megapascals. I'm going to do the same thing now for the 6 megapascals. So at 6 megapascals at 450, I've got an enthalpy of 3302.9, an entropy of 6.7219, and then at 500 degrees C, I've got 423.1 and 6.8826. So this is all the data I've got for my tables that kind of blankets. I blanket the temperature and I blanket the pressure. So what I'm going to do now is at 5 megapascals, I'm going to interpolate to find my values at 490. So I'm going to basically find 4/5 of the difference between these two. So I'd subtract the bottom one from there, multiply it by 0.8 and add it onto this one. And that will give me the value in the middle here of 3411.2. And I do the same thing for the entropy. 4/5 of the distance, or 40/50ths of that difference, gives me 6.9467. And I'm going to do the same interpolation at 6 megapascals to get my 490 value. Again, 4/5 of the difference of this two will give me 3399.1. And 4/5 of this distance here gives me 6.7873. So now I have the data at 490 for 5 megapascals and the data at 6 megapascals at 490. So I'm at the right temperature and I'm either side of it. So surprise, surprise, at 5.5 megapascals, so in between these two, I'm going to interpolate 50% of the difference between this one and this one. So basically halfway between these two to give me my final answer in here of 3416.9. And over here, it's going to give me 6.8670. So this is my enthalpy at 3. And this is my entropy, so that's S3 and that is H3. Okay, so far so good. So that's a double interpolation. You want to be comfortable at doing those. It doesn't get any harder than that. If you can do that, you're kind of all sorted. That means now that I have H3 and H2. So my heat into my boiler is going to be the M dot, the 25, times H3, which is my 3416.9, minus my H2, 207.3, and that gives me the heat into the boiler, if I can find that number, of 80,240 kilowatts, or over 80 megawatts. Which is one of the things they asked us to find in the question. So that's the heat into the boiler. So we've got the pump, we've got the boiler done. So the only component kind of left, well, there's a few more, but we only have to do one more now, is we're going to dive into the turbine. So you're starting to see the process now. We're going to draw the turbine. We've got steam coming in, water vapor coming out. So this is condition 3, condition 4. We've got work coming out of this. And what do we know? We can copy our conditions. So for 3, we just calculate this, H3, 3416.9. And then I actually did S3. If I hadn't, I'd have to go back and do it again now, but I've already done it. Is 6.867. And then at 4, we know the pressure at 4 is 10 kilopascals. If we go back to our graph here, or TS diagram, should I say, what do we know about 3 and 4? Well, we know kind of where 3 is. 4, in this case, it drops down. We don't know exactly where, because this is superheated, and we haven't dropped it directly down to the water. We do drop vertically down, though, because entropy in a perfect turbine is conserved. So the S value here has to be the same as the S value here. So S3 has to equal S4. That gives us that extra vital piece of information. Okay, so S3, so should I say S4 equals S3, which is 6.8670. And that is kilojoules per kilogram Kelvin. So that is the extra critical piece of information to recognize that for 100% turbine efficiency, S is the same. If it wasn't, if we had 80% efficient turbine, we would still find the ideal, and then we would use that to find the ideal workout, and we would multiply that ideal workout by the isotropic efficiency. But at the moment, this is 100% efficient, so we have S4. So what this lets us do is we can go to our tables for the saturated vapor tables, table A5, and we can go to the 10 kilopascal table. Let me grab that one. Because I'm fairly certain we're going to drop in. Sometimes you'll find that you can't find it. It's when you go to the 10 kilopascals. Let me get it right. Here we are. Sorry. We want an entropy of 6.8670. We go to 10 kilopascals and we shoot across, and we can find the entropy of the fluid, 0.6492, and the entropy of the vapor is just missing here, it's 8.14. So the value of 6.86 is in between those two, so we're definitely on this table. If our value of entropy here was above this value at 10 kilopascals, it would mean that we are still superheated after it came out of the turbine, which is kind of a waste of good steam. So typically it will drop in. So what we can do is we know we're on this table, and so we can write the, so let me, if I draw this again. So we know we came up, just a quick representation here. So we know that we've dropped back into here. So we are going to be at a quality, it's called a quality, a percentage of that distance across there. We know the value of this and this because that's the SF value and that's the SG value from our tables. So if we find that difference SG minus SF, and then we find how far we are to get our S value here, we can divide one by the other and we can find what's called quality, this percentage of the distance. So the way that works is we can write the equation that the entropy at 4 equals the entropy of a fluid at 4 plus X times the difference between SG minus SF. And this is all at 10 kilopascals. 10 kilopascals. So we know S4, 6.8670. We can read the SF value from the table, which, if I can find it somewhere, is 0.6492, as I just said, plus the X times the difference. And the difference is given in the tables as 7.4496. And we can solve this equation to get our X, and it turns out that X in this case is 83.5%. So what it says is we have come out of the turbine, isentropically we've dropped in pressure, and that superheated steam has gradually become wet steam with a little bit of liquid in. This is kind of low, 83%, so there's actually quite a bit of water in there, and in a real turbine that could be a problem. Little water droplets would start to smash the blade up. Really, you want to be 95% plus. But this is what we've got, so we'll work with this. What this allows us to do then is that the enthalpy at this point will also be X% of the enthalpy difference. So we can now find the enthalpy at 4. It's going to be the enthalpy of the fluid at 10 kilopascals plus X times the difference between the fluid and the vapor at 10 kilopascals. And so in this case, it becomes the 10 kilopascals, the 191.81, plus the 0.835 times the difference, which we get from the tables directly, 2392.1, gives us a value 2188.2 kilojoules per kilogram. So we have H4. Great. So I know the properties of in and out. Do my energy accounting equation. We're not storing energy, we're not creating it, there's no heat transfer. What we're left with is the work out of the turbine equals the mass flow times the enthalpy in, H3, minus the enthalpy out, H4. We know all of this. We have our 25 kilograms per second, times our H3, 3416.9, minus our H4, which we just found here, 2188.2, will give us the work out of the turbine as 30 megawatts, 30.717 kilowatts, or 30 megawatts. So that is the workout of our turbine. That was the H3. So we can wrap this up now. We've got, we could go and do the condenser the same way now. The condenser would be straightforward, but we don't need to. And we can dive straight to the efficiency of the overall thing. Efficiency, universal definition, what you want over what you pay for. Always works for everything in life. What do we want out of this whole system? Okay, when we run this engine, the steam plant, what we want, I've got my schematic here somewhere. We run this whole thing, we're going to put heat in. What we're really after is the work out the turbine, this W.T. So we want the work out the turbine. What are we paying for? Well, when we run this thing, we're paying for the heat into the boiler, and we're paying for the electrical work into the pump. This we're just throwing out, we're not paying for this. So the condenser heat rejected, we can calculate that, we don't need to at the moment, but it doesn't come into our efficiency equation. Basically this is going to be this plus this minus this. We can do that from an overall accounting equation, but it doesn't, we don't pay for this, we've already paid for it when we've bought it here as heat coming into the boiler. So what we're paying for is the heat into the boiler plus the work into the pump. So if I put these values down, what have we got? We have got the 30.717 megawatts coming out of the turbine, and we're paying for the 80.240 megawatts going into the boiler, plus the 0.3872 megawatts that would go into the pump. So I've just done it in megawatts rather than kilowatts. Doesn't matter. And that comes out to be 38.1% as the efficiency of this plant. Okay, so that's the last bit of the equation. If somehow we say we could use that waste heat that we're throwing out of this condenser, if we had a hospital nearby, or a university, or a prison, or something like that, or greenhouses that needed heat, then this heat we could actually feed into those, and because that is something that we want, the amount of heat that we get, we could add to the numerator here, and our efficiency would go up. Also, if we use that waste heat here, perhaps to heat the water up before it went into the boiler, that could also reduce the amount of heat required in the boiler, because we're recycling the heat from the condenser. So there are a number of things that we can do, and that comes later. We'll do TSD next year when we talk about optimizing these systems. But for now, that's a basic Rankine cycle. Worked our way around component by component, found states and properties either side of a component, applied our accounting equation, We applied energy accounting basically all the way. The turbine, implicitly, by knowing entropy is the same, we've effectively applied the entropy accounting equation here. We're not creating it, destroying it, storing it, so entropy in equals entropy out. So mass in equals mass out is pretty boring. The mass accounting equation is pretty uniform in this particular example. It's nearly all energy accounting with the exception of a little bit of implicit entropy accounting here. All right, that's a pretty comprehensive example, and hopefully that helps with your Rankine cycle. Thank you.